All right, so let's go ahead and take a look at, I'd like to take a look at the first 6 Webassign problems. So the first 6 Webassign problems look like this. Problems 1, 2, 3, and 4 are kinematics. Problems 5 and 6 deal with kinetic energy, right? The rest of the problems, 7, 8, 9, 10, 11, and then 14 and 15 are all force problems, force/torque problems. And so it should be pretty clear by looking at the problem distribution that the main topic in this chapter is forces and torques. So we'll take a look at kinematics, kinetic energy, see how those work in rotation, and then separately we're going to focus on force and torque problems. So let's see, number 1, a dentist drill starts from rest. These first 4 problems should remind you of what we were doing in chapter 2 when we had a truck. The very first problem was a truck slows down, and we have position, velocity, acceleration, and time. A dentist drill starts from rest. After 3.5 seconds, they're giving you the time, constant angular acceleration. It turns at a rate of 2.45 times 10 to the 4 revolutions per minute. What do they want you to find? Find the acceleration, find the angle through which the drill rotates. Find how far the drill goes. So what is this problem that they're giving you? Problem 1. Instead of a truck going straight, it's a drill rotating, but it's exactly the same idea. They're telling you the drill starts from rest. What does that mean? It means the initial speed is 0. They're giving you the time, and they're giving you the final speed. They say it rotates, rotates at a rate of 2.45 times 10 to the 4 revolutions per minute. I'm going to talk about that in just a moment. But revolutions per minute is telling you how fast it's rotating. They give you the final speed. They tell you the initial speed is 0. They give you the time. How many question marks are we going to have? Acceleration and our final position, which is also the distance. So how do you do these? Here's what I'm going to recommend. Use exactly the same strategy that we used in chapter 1. Lay out your information. And you might think, yeah, but it's rotating, so don't we have to rotate our information? No. No, the principles are still the same. If it makes you feel better to put things in a circle, you go right ahead. But the purpose of this strategy in chapter 2 was to organize your information so you could then write your equations. So you would have 2 equations, 2 unknowns, and you would solve. Sure, it's nice that visually it's linear motion, but now that we get to chapter 10, there's actually nothing in this strategy that requires us to rotate our information. If we just do this, we're just changing the letters. Now we're going to have theta 2, omega 2, and we're going to have alpha and t. Exactly the same idea, we just now have Greek letters. What do we have here? Always, we need to define where x equals 0. Our starting position, well, always just make it 0. They tell you it starts at rest. Starts at rest, therefore initial speed is 0. They give you the time. In this case, they're giving me 3.5 seconds. And they're telling me this is 2.45. I'm going to write it like this, and I encourage you to do the same. Actually, I'll write it out the way they gave it. 2.45 times 10 to the 4 revolutions per minute. A couple things that I don't like about this. I only use scientific notation when it is simpler, when it makes things simpler. There's absolutely no excuse to make things more complicated than necessary. This is 245.00. Notice, which is simpler? 245 times 10 to the 4th, or 245.00. Kind of an opinion, but I think the bottom is simpler to work with and look at. What about this revolutions per minute thing? Well, we use revolutions per minute quite a bit here in the US, just like we measure speeds in miles per hour. And so it is pretty common to run across angular velocities in RPMs, or revolutions per minute. You may have a tachometer on your dashboard next to the speedometer. That tachometer shows you the speed of your engine, how fast your engine is rotating in RPMs. but we need radians per second. So you're going to have to convert to radians per second. How do you do that? 245,000 revolutions per minute. Lay yourself down a couple conversion factors. We need to convert revolutions to radians. And of course, we need to convert minutes to seconds. This is not complicated. 1 revolution, 2 pi radians. 1 minute, 60 seconds. How does this come out? The minutes knock out, the revs knock out, you get radians per second. That's why we're doing it. But notice 2 pi is a little bit more than 6. 6 and 60. So therefore, it's kind of like dividing by 10. So very roughly, approximately, when you go from RPMs to radians per second, it's like dividing by 10. So if this is 24,500, it would be about 2,450 instead. It'd be a little bit more. I'm just going to do approximate. I'm going to go about 2,500 radians per second. Okay? So it's approximately 1/10. Anyways, convert this butter. What about our acceleration? Unknown. Theta 2, unknown. What are they asking you to find in this problem? They are asking you to find the acceleration and theta 2. So how do you do it? Exactly the same thing you did back in chapter 2. We have 2 equations. We have 2 unknowns. Write your 2 equations. What's the only difference? Well, we're using Greek letters now, but it's exactly the same thing. What do we have for our first equation? We're going to have theta 2 is equal to theta 1, which is 0, plus acceleration times time. Okay. And what's our other equation? Theta 2 is equal to theta 1, which is 0, right? Omega 1, which is 0, and then 1/2. You guys have done problems like this before. You've done problems where the initial position and the initial speed are both 0. So that's 0, that's 0, that's 0. You get V final is AT and X final is 1/2 AT squared. Where are the unknowns? Well, the unknowns are alpha, right? And theta 2. Use this equation to get your alpha, and then use that to get your theta 2. Done. Very simple versions of what we did in chapter 2. All right, so let's take a look at a couple more. They're going to go just as fast. Number 2, a centrifuge in a medical laboratory rotates at an angular speed of 3,700 revs per minute. There you go again, 3,700 RPMs. When it's switched off, it rotates 52 times before coming to rest. Find the angular acceleration. So what do we do with this? Well, get ready to set up your information. What are you going to need? Theta, omega, right? Alpha, t, theta, omega. Okay? What do they give you here? It starts off at 3,700 RPM. So we have 3,700 RPM. Of course, your initial position is 0. And then it comes to rest. So at the end, it's not moving. But they tell you it rotates 52 times. What are they describing? They're describing how far it goes. They're describing its rotational distance. It rotates 52 times. So what they tell you is, after it's traveled, its final position is 52 revolutions. What do you need to do? You need to convert this to radians per second. But you also need to convert this to radians. You know there's 2 pi radians to a revolution. This needs to be in radians, right? They're kind of playing around with the units there. Great. Acceleration, unknown. Time, unknown. Just like we did in chapter 2. How many unknowns do you have? 2 question marks, 2 equations, write them out, solve. This is excellent review. It takes you right back to chapter 2, and hopefully when you're doing this, you're going, oh wait, I remember doing that. And that serves 2 purposes. It reminds you that you do know what you're doing, but it also reminds you that we got a final coming up in a few weeks, and you know what you're going to be doing for that. So it's a good review of the stuff that we've done. If we write our equations, once again, we get V final, which is omega 2 is 0. So we get a 0 equals omega 1 plus alpha t. And then we get x final, which is theta 2, is equal to 0. We get omega 1 times t plus 1/2 alpha t squared. Where are your unknowns? Well, your unknowns are alpha t, alpha. So how would we do this? We should make a plan. And here's what I think the plan should be. First equation, rearrange it to read alpha equals stuff. Then sub into the second equation. Your alpha is going to equal minus omega 1 divided by t. You can sub that into here and then simplify, and you can calculate your t first. The problem doesn't ask you for t, but you're going to get it first anyway. So solve for t, get t, and then you can use it to go back and calculate your alpha. Let's see here. Number 3, a rotating wheel requires 3.07 seconds to rotate through 37 revolutions. So let's go ahead and take this out. You know what we're going to be doing. I won't erase the whole thing. Let's go ahead and get rid of this. Like that. This is going to be number 3. A rotating wheel requires 3.07 seconds. Here we go. 3.07 seconds. We got a 0 for the starting position. To rotate through 37 revolutions. Here you go again. It's going through 37 revolutions. That is the distance. So we have 37 revolutions. Of course, you need to convert that to radians per second. Its speed at the end of the time, its speed at the end of the interval, is 97.7 radians per second. So we have 97.7 radians per second. What is the acceleration? So they're asking you to find the acceleration. What about the initial velocity? It's tempting to want to put a 0 here, but this is why following this strategy is so crucial. When your brain does things like, oh, I'll put a 0 here, this allows you to go, no, wait, that can't be right. Because what do you know about this? You must have 2 unknowns. You will have 2 equations. You must have 2 unknowns. What does that tell you about this? They didn't tell you it's 0. It's tempting to want to fill in a 0, but you know it can't be 0. You know you need a question mark right there. So in this problem, there's your 2 unknowns. What do? Write your 2 equations, solve. Just like with the last problem, number 2, you'll have alpha and omega 1 in both equations. So I would solve the first equation for omega 1 equals, and then sub that into the second equation. It's essentially the same process as we just did for problem 2. I am losing some daylight here, folks. The weather's been a little cloudy, a little rainy this weekend. Makes it kind of hard to get the lighting I need to do some decent video. So let me check something real quick. Okay. Yeah, we'll see how it goes. I'm just concerned that I'm losing decent lighting here. All right, let me go ahead and do number 4, and then I'll see how it's looking at that point. See if we can get through all the first 6 here. So number 4 has a CD. A CD, same principle for a DVD or any laser disc. The shiny surface on that disc actually has a microscopic spiral of tiny little pits, microscopic little pits. And the idea is, as the disc spins, the laser of the player hits those discs, and the reflections are what's picked up by the reader, and those reflections are turned into a digital code, which of course is then converted into either music, movie, or whatever is on that disc. So they're giving you some information here, and they want you to sort out the information. What they're telling you is the spiral of these pits starts here, and it spirals outward till it gets to the edge out here. And what they tell you is that, this is number 4, that the disk turns, the disk is rotating in such a way that the laser that's reading it, the lens that's reading it, the track moves above that lens at a constant linear speed. So they tell you, you have a constant linear speed, and the value they give me is 1.30 meters per second. Your number will be different, of course, or could be different. But they say, at the beginning, when you first start playing the CD, or the disc, whatever, the read head is right here, the lens is here. As the disc plays, the head has to move outward so that it tracks the spiral, so the spiral stays underneath it. And at the end, it's underneath this point. So I'm going to call this R1, and they give you R1, and I'm going to call this R2, and they give you R2. I'm also going to say that this is V1, and this is going to be V2. Notice what I've done here. I've identified a point. The beginning of the spiral is a point on a rotating object, and the end of the spiral is a point on a rotating object. And what do we know about these points? They are rotating, they have rotational motion as part of the rotating object, but they also have corresponding linear motion that we can connect. So they're telling you V1 and V2 must be this speed. But what they're asking you for is, what is the initial angular velocity at the beginning? And so what they're asking you to do in the beginning is connect the rotational motion with the linear motion of this point. Just make that connection. They give you V1, they give you R1, and they say, can you tell me what omega 1 is? That's the initial angular velocity at the beginning. Similarly, at the end, they're saying now that the lens is out here above this point, we're interested in this point on the rotating disc. We have its R2, and we know its V2 must be the same V. That's what's given to you in the problem. So can you calculate initial angular velocity, omega 1, and final angular velocity, omega 2? Yeah. Then what does the problem give you? Then the problem says, all right, it takes 74 minutes, 33 seconds to get spin, all the way to there. They're telling you how much time it takes to get from that speed to that speed. And what are they asking for? Part C, they say find the acceleration. Part D, find the total angular displacement, or the angular distance. So what are parts C and D doing? Now they're asking you for the distance and the acceleration. They're giving you the time. What is being handed to you here? It's exactly the same thing that we just did for problems 1, 2, and 3. So for parts C and D, what do? Make this. What you should recognize is parts A and B are, hey, get these two. Get omega 1 and omega 2. And then what? They give you the time. You have to convert that into seconds. They give it to you as 74 minutes, 33 seconds. Right? Yeah. So you have to convert that into seconds. But it's now, part C and D is just a motion in one dimension problem. Can you write your two equations? And then, can you solve for theta 2 and alpha? Which I believe are the same thing we did in problem 1, the dentist drill. Do I get that right? Yeah. Number 1, it's exactly the same thing. Number 1, the two unknowns were alpha and theta 2. So there you go. It's exactly the same thing as number 1. What is part E? Part E is what I call a curveball. And curveballs are really important if you're planning to do anything like the MCAT or any kind of standardized tests, because the people that write questions for those tests, they love throwing curveballs at you. Even sliders, change-ups, everything. They love to be able to see what you can hit. And so you need to practice curveballs. You need to practice hitting these and see them for what they are. So this entire problem so far has been, hey, point on a rotating object, linear motion, angular motion. Same thing here. Hey, rotational kinematics. Can you do this? In other words, this is all the stuff we've been talking about. Can you do this? We get to part E, and your brain is on this track of this is rotational motion, right? What comes next? Your brain is primed for chapter 10. The curveball to part E is that it has absolutely nothing to do with chapter 10. And it's important to be able to recognize that. It's important to be able to recognize when your brain is primed and expecting this, but then you're given this, it's important to recognize what it is and not be distracted by your expectations. So, what is part E? Part E says, what is the length of the track? How do you get that? Take a step back and look at the information. They tell you that the track is moving at 1.3 meters per second under the read head, under the lens. And they tell you the amount of time that it's going for. Now you can imagine the lens is basically following the track. The lens gets 1.3 meters of track every second for this many seconds. Can you tell me how many meters long that track is? That's the speed, that's the time. Get me the length of the track. That's it. So that's number 4. I'm really unhappy about what's happened to my lighting here, folks. Man, it's only mid-afternoon, and it's just, I had some sunshine just a little bit ago, which really lights up the room, but let me, man. I'm gonna go ahead and shut this video off and pick it up when I have some better lighting. All right, so I'll see you guys in a little bit.